Hey everyone, welcome back to Math 20-1. We are into Unit 2 and we are going to start our unit with solving systems graphically. Remember, you can stop the video at any time to get in touch with your teacher. Let's get started. Well, to start, let's remind ourselves that to solve an equation simply means to find the value of x that makes the equation true. This means that if we put in that value of x, the left-hand side will equal the right-hand side. So I want you to start by pulling out some of your quadratic skills from the last unit and solve this equation and verify that the solution makes the left-hand side equal to the right-hand side. When you're done, pop back and see how you did. Well, let's check it out. So you isolated the x, and the big important thing here is to remember to take the plus minus here. Remember, when we take the square roots in this course, we have to take plus minus, or we might miss one of the solutions. For instance, here there's two solutions, plus 4 and minus 4. So when we plug these in, taking the plus 4 first, sure enough, the left-hand side equals the right-hand side, and you should have got 18 equals 18. Same with the negative 4. Negative 4 squared is the positive 16 plus the 2, and we get 18 equals 18 again. Now, suppose you were asked to solve this equation, x squared plus 2y equals 18. Well, you can't, because both y and x are unknown. We don't know two things, and we have nothing to compare it to figure out the other one. So what does this mean? It means that depending on a value of y, there could be many values of x that solve the equation and vice versa. Meaning I can choose a value of x, like x equals to 4, plug it in, and I find that y equals 1 would make this statement true. So this would be an ordered pair that's a solution to this equation. But I could find other solutions as well. But y equals 5 and y equals negative 3.5. And so would x equals 3 and x equals 4.5. You can check it out, see if it works. In fact, we know this is the equation of a parabola. We've learned this in the quadratic unit. And any point on the parabola will satisfy the equation, meaning there are going to be infinitely many points on the parabola, and there are actually infinitely many solutions to this equation. So trying to state the solution is actually impossible. However, what if things were a bit more restricted? What if the values of x and y had not only satisfied this equation, but what if they're going to satisfy this one? What does that mean? Well, this means we want an x and y that if we plug it in here, or if it plugs in here, they will make both equations true at the same time. I want you to give this a try. I'm going to tell you there are actually two solutions, negative 2 and 7, and 2 and 7. I want you to check for yourself. Do these by values? Do the values satisfy both equations? Check it out. Does the left-hand side equal the right-hand side? Pause the video, come back, and see how you did. Well, how did you do? So you may have figured out you have to do this 4 times, because this solution you have to check not only in the x squared plus 2 equals 18, but you also have to check it in the y minus x squared equals 3. And you have to do that with this solution here as well. And when we did it, I was sure enough able to find that the left-hand side equals the right-hand side in these two equations. If you want to pause the video and just check over your work. noticing that negative 2 squared is that positive 4, 7 minus 4 equals 3. We have 4 plus 14 over here, still equals 18, and 3 equals 3 here. So we were able to show that both solutions satisfied both equations at the same time. Well, these two equations are what is known as a system of equations. In other words, a system of equations is when two or more equations made of the same variable are together. For example, x plus 3y equals 6 and y equals 7 minus 2x. The solution to a system of equations are the values that make both equations in the system true. And as long as there are many equations as there are variables, in other words, for instance, 2 equations, 2 unknown variables, 3 equations, 3 unknown variables, these systems can be solved, unless it has no possible solutions, which sometimes can be the case, and we're going to look at some of those. Now, on a graph, an ordered pair, x and y, where functions intersect, is called a solution to the system. So let's look, how can we graphically solve systems of equations? Now remember, any point on the graph of a function satisfies the function's equation. For example, how could we confirm that 2 and 5 is on the graph of y equals x squared plus 1? And how could we confirm that 3 and 7 is not on the graph? Well, easy enough. Let's graph it. Well, notice 2 and 5 is on the graph where 3 and 7 is not. Now let's think about what this means for systems of equations. Remember, we're trying to find values of x and y that make both equations true at the same time. We can think of these x's and y's as points, or ordered pairs. Now we know that the x and y's must lie on the graph of one equation, as it needs to satisfy that equation. But if it's the solution, xy must also lie on the other equation's graph, as it needs to satisfy that one too. So in other words, this point, x and y, is or are on the graph of both equations. Now, points that are simultaneously on the graph of two different equations, what would this look like? Look at the following graph system of equations. Which points are on both graphs? Take a moment and mark on your paper where you think those are. Well, if you said that these points would be the ones where the graphs are intersecting, you would be right. In fact, this is the same system of equations that we began this lesson with. These are the graphs of x squared plus 2y equals 18, which is the red, and y minus x squared equals 3, which is the purple. And remember, in those ones, we said that the points were negative 2 and 7, which is right here. And the other one was 2 and 7, which is right here. And these were the points that actually satisfied the system of equations at the same time. So this leads us to a big idea. Since any solution to a system of equations simultaneously satisfies both equations, the solution will be found at the intersection of the two equations' graphs. Now, the systems of equations we will study in Math 20-1 will either have 0, 1, or 2 solutions. In one specific case, they could also have infinitely many solutions, and we're going to be looking at that too soon. So let's keep going. Now, keeping in mind that the solutions of these systems can be found by observing where the graphs of the equations in the system intersect, I want you to kind of think about what this means. Sketch some examples of graphs for systems of equations that would have the indicated number of solutions. So 2 graphs that would have no solutions, 2 graphs that would have 1 solution, and 2 graphs that would have 2 solutions, keeping in mind that the intersection is considered a solution. Come back and see how you do. Were you able to do it? Did you find two graphs that had no solutions, 1 and 2? Well, let's look at these examples and see if yours kind of look like these next two. So imagine a system of equations with each of the quadratic functions below and one other function. In part A, we're going to look at if the other function in the solution is linear. Could you have no solutions? Well, let's think about that. Let me get a line out here. Well, what if we had a line that went like that? Well, in this case here, these two would never cross because the quadratic is going down and away from the line. Could we have one with a linear with one solution? Well, let's see. What if we took this line and we just kind of moved it down so it was just touching the vertex like that? Well, there we have one solution. Did your graphs above look something like this? But what if we took the graph and the line and moved it down a little further? Well, now we have two solutions because we have 2 places where it crosses. So in other words, if it doesn't touch, there's no solution. If it just touches, there's one solution. And if it crosses in 2 places, it's not no solution. It's 2 solutions. Let's fix that up a little bit. Okay. Now, what if the other function in the system is quadratic? Could you have no solutions, 1 solution, 2 solutions? Let's see what we come up with. Well, the first one, let's change the color up. Let's go green. Well, what if we had almost the exact same graph, but rather than going up, it was going down? Just like that. Well, this one, with the red one, there are no solutions because there are no intersection points. Well, how could we make it one solution? Well, what if we just went ahead and had it come up and just touch at the vertex? Well, this one right here would be one solution. And then if we wanted to have 2 solutions, we would go up and come down again so that we would have 2 intersection points. And this one would be 2 solutions. Let's keep going. Now, what happens if both quadratic equations produce the same graph? How many solutions are there? Well, that should have really been up here. So what happens if they have the same graph? What if I took one of my things? Let's get another color out here. What if I took a graph and laid it right on top? I know this doesn't look like it, but use your imagination. That this one is exactly on top of the red one. How many solutions are there now? Well, if you said that there was infinite, you would be right. And we could say when there are overlapping graphs, there are infinitely many solutions. Well, let's keep going here. Let's look at the example. What are the solutions of the system of equations shown below? The equations graphs are also shown. Well, you may notice that these two equations have two intersection points here and here. That means that if we find those points, well, this one here is actually it's a y-intercept because the ordered pair here is 0, and each of these represents 2, so -2, -4, and -6. So that is one solution. The other solution is actually an x-intercept, which is at 6 and 0. So these two would be solutions, and we can always verify these things by going ahead and showing that the left-hand side equals the right-hand side. And if we go ahead and do that, we plug in our x for the first one, so 0 squared minus 5 times 0 minus 6 equals -6. And on this side, we're substituting in -6, and sure enough, the left side equals the right side. Now, it's not enough just to check one of the points with one of the equations. We have to check each point with each equation. So this one, we're going to try with the linear one. We're going to still use our 0 and -6, but we have to check it with x minus 6, and that equals y. Now, I notice I switched away the left-hand side and the right-hand side, so you pretend that we switch these up here. Okay, so x is 0 minus 6, which is still -6, and y is -6. So again, the left-hand side equals the right-hand side. And if you want to, go ahead and check the other point to see if that also has results in left side equal right-hand side. Now it's time for you to try. Open up the practice questions, and I want you to try 5A and check your answer at the bottom. If you're an asynchronous student, please make sure you let your teacher know how things are going. They want to hear from you. Take a moment and then come right back, and we're going to look at something else. Okay, so let's solve the following system equations graphically by hand, and then we're going to verify the solutions with the calculator. So let's go ahead and we're going to set up a quick little table of values. Now, when we set these things up, we want to make sure we have a good variety of values. So I am going to pick the x values here. Let's call this y1 and y2, so we can just put everything on the 1. So up y1 there, y2 there. Now y1, we're going to pick, let's see here. Okay, so let's pick some x's. Let's pick some going from -2, -1, 0, 1, 2, 3, and 4. So let's sub them into y1. So -2 minus 4 is -6. Now, if we use the same method and fill this in all the way down, we actually get something that looks like this. Let's do the same thing for y2. This time we're going to substitute in -2 And that solves to give us 0. And if we follow the same procedure all the way down, we would get -5, -8, -9, -8, -5, and back to 0. So let's put these things together. Well, the first one there is linear. I'm going to use my little linear graphing thing here. And I know that the first one goes from -2 and -6, which is there. And it has to go up to 4 and 0, which is right there. But let's just keep it going like that. And this one here is going to extend that way. Now, the quadratics ain't going to look so pretty. So let's use red. And we have -2 and 0. We got -1 and -5. Oh, look what's going on there. And then we got 0 and -8. 1 and -9. 2 and -8. 3 and -5. Oh, and 4 and 0. So when we graph that, we get something. Oops. Pretend that goes through. Let's try that again. Oh, some days you just can't do things right. I'm really bad with this pen. We're going to pretend that I got those to go through all those dots. There we go. But the thing that we can see is that we have two solutions that are the same. And that's because when x equals -1, y1 and y2 equal -5. And when x equals 4, y1 and y2 equals 0. Now we can definitely go ahead and verify these things graphically. So let's use our graphing calculator. Put x1, x minus 4, x squared minus 2x minus 8 in the calculator. If you need to pause the video to do this, go right ahead. Now, when we hit the graph, this is what we get. Now, it looks kind of similar. Now, we're going to find the intersection points here and here. Now, we can do it using second trace, and we're going to use number 5 for intersect. Well, this is the first graph. Notice I'm closer to this first intersection point. So I hit enter, and now I get a little closer to that intersection point again. I hit enter, and it gives me -1 and 5, which is this one up here. Let's do it again, but let's do it for the other intersection point. So second, trace, number 5. Remember, if you are working on your own, the instructions are just above. This time, notice I'm moving over closer to this one because it's going to look for the one that's closest. So we're going to go over here. Now we've jumped down to here, so let's get a little closer again. And now we get 4 and 0, which is this one right here. So writing these down as the solutions are -1 and 5 and 4 and 0. Let's try another one. Solve the following systems of equations graphically and verify the solution algebraically. Well, the first thing to solve graphically is, first step, rearrange to isolate the y. In this one, I'm going to add y to both sides, and I'm going to add 35 to both sides. All that's going to do is going to give me y equals 2x squared minus 16x plus 35. Then I'm going to repeat the process for the one down here, and y equals 2x squared minus 8x plus 11. So let's go ahead and put those in the calculator. We're going to delete what we had before, and to put them in, We're going to go 2, and remember the X button is right here. Squared minus 16x plus 35. And go down to the next one. 2x squared minus 8x plus 11. And hit graph. There's one, and there's the other. Now, if we change the window settings a little bit on the Y, let's make it from 0, and let's put this up to 40. That's just going to let us see some of the other features. So there's that one going through the Y-intercept, and there's the other one right there. Notice this one has one intersection point right here. We go second, trace, and we find 5 for intersect again. Just by the shape of the graph, the shape of quadratics, we have the solution is 3 and 5. Well, we want to verify this. So we're going to take 2x squared minus 16 minus y as our right-hand side, and we're going to compare it to the left-hand side of negative 35. So let's sub in 3 and 5. Oops, forgot my x. Well, this is 2 times 9 minus 16 times 3, that's minus 48. Well, 2 times 9 is 18, minus 48 minus 5 is minus 53, and minus 53 subtract 8, or 18 minus 53 is minus 35. So left hand equals right hand. Let's make sure it works for the other solution. Well, we got the right-hand side and the left-hand side. 2x squared. This time we're going to put the minus 8x minus y equals negative 11. And we go 2 times 3 squared minus 8 times 3 minus y, which is 5. Well, 2 times 9, still 18. And 8 times 3 is minus 24 minus 5, which is 18, minus 29, which is minus 11. So we have negative 11 equals negative 11. So the right-hand side also equals the left-hand side. So this is the solution to the system of equations. So for the next one, same idea. We want to solve the system of equations and verify the solutions algebraically. Okay, so we're going to plug these into our calculator, but the first thing is we have to get that negative y to the other side. Same with this one over here. So we get two equations, which is y equals negative 3x squared minus x minus 2. The other one is y equals 6x squared plus 4x. So we go ahead and let's get our graphing calculator out. Y equals, the first one is negative. Remember, we use the negative 3x squared minus x minus 2. And 6x squared plus 4x. We hit graph. Oh, there's one. And I can't see the other one. Let's go ahead and reset our window settings. So a quick way to do a reset is go into Zoom, and you can either scroll up or down, but we're going to go 6 for standard. And here we go. Let's try it again. Oh, wait. Look what we got right here. Notice here, this graph, Kind of looks something like this. But this graph looks like that. Oh, what do we notice? We notice here there is no intersection. And when there's no intersection, that means there is no solution. And because there's no solution to verify. Let's keep going. I want you to take a moment now just to check in and see how your understanding of solving graphically are. I want you to try question 5A from the practice questions. And again, get in touch with your teacher if you need any help. Okay, let's look at question 4. And it's asking us to write a system of equations to model the quadratic equation. Now, you've seen quadratic equations before. And normally what you would have done is you would have taken everything and brought it to one side to make the other side equal 0. And you could have solved for x by going ahead and factoring or using the quadratic formula. But we can also solve this quadratic equation by creating a system of equations and solving that. The way we're going to do that is make one side equal to one equation and the other side equal to the other equation, because notice these are equal to each other. So that must mean right now, writing it as y equals, this is actually the same y. So let's go ahead and graph that on our calculators. Well, when we put that into y equals, we might have to adjust our window settings a little bit. I think I made my max window 20. There we go. I can see I have two solutions here and here. Again, we go second, trace, and 5 for intersect. Now we're going to go close to the first one, enter, enter, enter. And notice we have some decimal values. So in this case, x equals to the nearest, let's say the nearest hundredth. Let's do that. X equals negative 1.81 when y equals negative 2.2. And I think it was 2.21. Oh, negative 2.24, round to 5. Now let's get the other number. And we go, oops, second trace, and we're going to head out closer to this one now, so that it's going to be looking up this way. Enter, oops, second trace. It's just going to be one of those days. Second trace, 5 for intersect. Good grief. I don't know how my window settings have changed, but we're just going to go with it. And we get 3.31. And the y value there is 18.25. Now remember, this is a little different because here we are only looking for x's. So the solutions here, while these are solutions to the system, we are only looking solutions to the equations. Therefore, the solution to the equation, actually solutions, is x equals negative 1.81 and x equals 3.31. Determine two integers that have the following relationships. 14 more than twice the first integer gives the second integer And the second integer increased by 1 is the square of the first. Write a system of equation that relates to the problem and then solve graphically. Well, the first thing we have to do is we have to identify two integers, and one being the first and the other being the second. And now we're going to make some math statements given what we've been told. 14 more than twice the first. Well, twice the first is 2x, and if we have 14 more, that's add 14, and that equals y. Well, then they said the second integer. Well, the second integer is y, and we're going to increase it by 1. And that's going to equal the square of the first, which is x squared. Now, we want to solve this graphically, but before we do, we have to rewrite the second equation in terms of y. So y equals x squared plus 1. And we're going to put those two in our calculator. Now, going ahead, we're going to say 2x plus 14. And the second one is x squared minus 1. And let's hit graph. Well, there's the first one, and there's the second one. Now, I can tell there's going to be another intersection point, so let's change our window setting. We're going to change it so that our y max is only going to be 0, because we don't need to go that far. I'm going to triple this one right here, just to be sure. And there we go. There's one, and there's the other. So I can see my two intersection points. So I go second, trace, 5 for intersect. Now I want to get closer to one than the other. That's going to tell me I'm going to look for this one over here. So the first one is -3 and 8. So let's write that down. That's one solution. -3 and 8. The next solution, well, let's go over and do it again. Second, trace, 5 for intersect, and go over here. Scroll it all the way close. Hit enter, enter, and do it again. And now that one is 5 and 24. And you can verify that you've done this correctly by making sure the left-hand side equals to the right-hand side. In other words, we want to show that 2x plus 14 equals y. And we want to show that y equals x squared minus 1. And we want to do it for both of these points. We want to test -3 and 8, and we want to test 5 and 24. So that's the end of this lesson. If you have any questions about this, make sure you get in touch with your teacher. I hope you have a great rest of your day. Take care.